Welcome to a new video about analog filter design. In this example we will discuss the Inverse Chebyshev low-pass filter design. We will use the state variable circuit for our realization. Of course we will see everything step by step in our calculations and verify these in SPICE simulations. Okay, our design objective is shown here. We would like to design an Inverse Chebyshev active low-pass filter, and we will use a state variable filter circuit. And the DC gain we need to have is 1 or 0 dB. The specifications for this filter are shown here. The maximum passband ripple is 1.5 dB. The minimum attenuation is 20 dB. The passband frequency is 1 kHz and the stopband frequency is 2 kHz. Now the meaning of these specifications are as follows. At this frequency, stopband frequency of 2 kHz, we need to have a minimum of 20 dB at least. And there is a specific passband frequency. We will see shortly in the calculations also that the gain is max 1.5 dB. So it can be lower, but this is the maximum allowed. Okay, let's see how we do this design. First, calculations. In order to go on, we first start with the filter order, very important step. And for that we need to relate our A max and A minimum to the epsilon P and epsilon S. We will see shortly. Again, the same formulas as we have done for the low pass filter designs for our Bode and the Chebyshev response. We see here again the A max. We substitute here the values and you get here 0.6423. Epsilon S, relate that A minimum. Again, you substitute here 20. You get here 9.9499. Now taking this together, we will use exact same formula as for the Chebyshev response for the low pass filter. You see here again the R cosine H and the epsilon S and epsilon P we just calculated, and our Fs, stopband frequency, and the passband frequency. You substitute here the values, you get here 2.6063. That means we need to go to an integer. That means we need to use an NF3, so third order inverse Chebyshev response active low pass filter. Now the second step is to normalize Chebyshev poles, natural frequency, and the quality factor per stage. Now the procedure for calculating the component values for the inverse Chebyshev response goes a little bit different than the calculation we have done for the Bode and the Chebyshev using the tables. In this case we really need to go to the details about the poles and natural frequency and cutoff frequency and also the quality factor, so that is actually really what we need to do here. Okay, but we start with the Chebyshev poles and then we will convert that to the inverse Chebyshev poles. We will see that shortly. We start with the normalized values, so normalized Chebyshev response. Those are given by this expression. These are the poles. You see here the real part and the imaginary part. Again, I leave the details out, but this is how it is. And you see the pole and the K, which is then the pole number, and the N is all filter order. Now in this case we need to go for N3. There is also a parameter A here in order to make this formula readable. So it is actually a more and larger formula. You see here again this epsilon S is appearing and the filter order again in this expression. In this case we can already substitute the values in order to calculate this A, and that will result in 0.9977, almost 1. So that goes in here and in here, and we also need to now calculate the poles. So for a third order filter and a 3, we have one real pole and one complex conjugate pole pair. So this will be a complex pair or complex conjugate pole pair, and this will be just one real pole. So we have again in total 3 poles, and the poles are given as follows. So for K is 1 and 3, those are actually a pair, so a complex conjugate pole pair. You substitute here K is 1, and also here, and also the A value we just calculated. Of course also this filter order here, that will be then 2 times 3, will be 6. You do the calculation, you get this expression here. So you see here the real and the imaginary part. If you do that for the 3, for K3, you get the exact same. The only difference is that you get them minus J, etc. For case 2, you get exactly this result, or this is the real value, so you don't have any imaginary parts here. Okay, so we have our poles. Now, the Chebyshev poles are located on an ellipse. That is actually what you can see from here. If you draw that, you will see that you have an ellipse. And the design is then composed of 2 stages in this case, because we have a real pole that needs to be designed or realized. And there is also a complex conjugate pole pair that is also what we need to realize. The natural frequency is given by this expression. In general, you see here the n, omega n, this is not the filter order, so don't confuse that as the natural frequency. The t here is referring to the stage numbers, so stage 1 and stage 2. And the quality factor is also given here, and it's again the t same stage number, again the natural frequency divided by the 2 times the sigma t. What is all this meaning? So the omega, I mean the sigma here, is the real part of your pole. And the omega is here the imaginary part of your pole. In a similar form, you also use that for the quality factor. Now again, here you see that t is the stage number, the sigma is the real part of the Chebyshev pole, and the omega is the imaginary part of the Chebyshev pole. So our first stage, we start with this complex conjugate pole pair, and those are the poles 1, 3. Now for the natural frequency, we can use this formula. You can again use here the t is 1. You see here then this will be a 1, this will be a 1, and you refer then to this pole pair. You see here 0.5859. Of course you can take the minus, but it will be squared, so it's not necessary. And there will be also this 1.3341, which is then the imaginary part. Now if you do the calculation here, you get here 1.4570. Now the quality factor, we know this. We can now use again the values from the pole real value here in the denominator, and you get here 1.2435. Okay, now for stage 1, the calculations are done. Stage 2 is a real pole, so this is actually pretty straightforward, but I would like to show you that in detail what happens. The natural frequency for this pole is really the real part again squared plus the imaginary part squared. Taking this together again, the same format and the square root of that one. Of course, since there is no imaginary part here, that is effectively just this 1.1717. So this actually just copy this, and that is what you have as the natural frequency. And the quality factor is normally always a half for the real poles, but I will show you how you do that again in a similar form as we done it for this stage 1. You see here indeed that this is producing as 0.5 or a half. So if you have a real pole, you can already say the quality factor is 0.5 and your omega n, or your natural frequency, is directly the pole location. Okay, now taking this together, we have now here the stage 1 in summary and stage 2 in summary, the results. Now we need to go to the inverse Chebyshev natural frequency and the quality factor per stage. So from here we need to convert that to the inverse Chebyshev parameters. Now the quality factor of the inverse Chebyshev response, which is given by this q sub t to the power minus 1, which is referring that inverse Chebyshev, is the same as the quality factor of the Chebyshev. So if you have this will be also for the inverse Chebyshev. So that's actually given here. But for the natural frequency of the Chebyshev, inverse Chebyshev response, that is given by this, is the inverse, really the inverse of the natural frequency we have calculated here. So that's actually given by this expression. So again, the t is here the stage number. Now for each stage we can then write it like so. And also the poles are given by p1, 3 to the power minus 1, referring to that inverse. Here you see the natural frequency, so the natural frequency for our inverse Chebyshev response is 1 over that, what you see here, so 1 over this 1.4570, that is this, and the quality factor is really just a copy of what you have here. For stage 2, similar form, again the P2 will be then inverse, so that will be then again this to the power minus 1, just to refer that, and then you get here 1 over that, and you get 0.8534. The quality factor is exact same as before, so we take here 0.5. Okay, now step 4 is the normalized inverse Chebyshev response zeros. We have zeros in order to create the ripple actually in the stop-at region. That is the fundamental difference between the Chebyshev response and the inverse Chebyshev response, because the ripple in the Chebyshev response was in the passband, and for the inverse Chebyshev response it will be a ripple in the stop band. So in the passband you will not see a ripple. That is of course very nice. So it looks like a Bode response. So we need to go for the zeros, that is actually creating this ripple in the stop band. Now the zeros are given by this formula. Again, I leave the details out. You see here the omega z, which is referring to that zero frequency, and the t is again here fill the stage number. So 1 over this cosine expression here with this n filter order, T, which is our stage number. Now we have NF3, so we can already say that this is the 1 over this, and then a cosine of this expression divided by 6, because 2 times 3. And now we can go for the stage. Each stage we can calculate the zeros. So stage 1, this one, we know that k is then 1, so we can just substitute here. K is 1 over here, and you have here your result, which is then 1 over cosine of pi over 6. And that is here given 1.1547. Okay, how about stage 2? Now we should have, in theory, the number of poles are equal to the number of zeros in a transfer function. Now, if you now go to the k is 2, that is then here omega z2, that will be then 1 over, now 2 times 2 will be 4 minus 1 will be then 3 pi over 6. So it will be then pi over 2. The cosine of pi over 2 is 0, so that means this goes to infinity. So there is a 0, but that is in the infinite. So that's actually what you see here from this calculation. So the summary of the results so far for our normalized values of the inverse Chebyshev response are shown here for each stage. You see the quality factor, the natural frequency, and the zero frequency. Now, in order to go to the actual component values, we need to do the denormalization of our inverse Chebyshev response. For that, we will need to denormalize the natural frequency and the zero frequency per stage. Now, we have the frequency scale factor, and that is now in this case the omega s, which is then this 2 pi times this stop band frequency. That is given by kf, so 2 pi times the stop band frequency will be then 2 pi times 2000, so 4000 pi radians per second. In this case, we do this in a little bit different way than the Bode response and the Chebyshev response, frequency scaling. Now we get the situation where you have the stop band attenuation exactly at 20 dB at that frequency. So at this 2 kilohertz, we will get exactly this 20 dB in this case, but we will fall below the maximum allowed passband ripple, which is of course fine, because this is maximum allowed, in this case 1.5 dB. So it can be the case that we have just 1 dB or 0.7 dB in this case, but we will get a minimum exactly at the 2 kilohertz. Okay, using these values, now we can do the denormalization for stage 1 for the natural frequency and the zero frequency. You see the formulas, you see the kf and the kf here. Now we will use this hat on top of it. That is really to distinguish that from the denormalized values. Of course, it's getting a little bit crowded with the subscript and superscript, etc. So I try to make it more readable. But you need to use these values here and then multiply that by kf. You see that, and you get this value for the natural frequency here denormalized. Similar form for the zero frequency for the first stage. Now for the second stage, since this is the passive low pass filter, RC, so we can go directly with the natural frequency. There is no zero frequency there, which is at infinite, by the way. Again, we will take this value, 1.1547, again, multiply it by kf, you get this radians per second for the natural frequency. Now we have done our denormalization, so we can now summarize that. So the normalized values will be now shifted to the denormalized values. Okay, now we go to the next step, which is our circuit realization and the component values. So we will jump to that. So this is the circuit we will use. It's given here. This is the state variable filter circuit. You see here a couple of operation amplifiers and a lot of resistors and capacitors. We will see shortly how we do that for each stage. And these are the normalized values we have calculated again in summary for each stage are shown here. Now we start by selecting the resistor R as 100 kilo ohm and the capacitor C as 100 nanofarads. And those are shown here. So we have here R, 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 so 4 R's. And we have also 2 capacitors called C. Then we can calculate the other component values. Now we start with the first stage, stage 1. That's, by the way, the state variable low pass filter circuit. And if you ignore this C6, that is actually what we do. The C6 and the R6 are required for the stage 2 calculations. Now, R1 is equal to R2. That is the first step in this stage 1. So we set these two resistors equal to each other and calculate that using this formula. Again, taking the values from the table here, the quality factor and the natural frequency. And by the way, these two, and the capacitor C we have selected as 100 nanofarads, and it will result in the value here. The R2 and R3 are calculated using this formula. So again, the natural frequency and the capacitor we have selected, and you see here the value. R5 is calculated using the resistor we have selected, so 100 kilo ohm, the quality factor first stage, the zero frequency and the natural frequency, and the result will be here, so 43.93 kilo ohm. The required DC gain in our design was 1 or 0 dB, and that means for our calculations the K, which is then the parameter we'll see shortly, is set to 1 here. Now that is then given here, so the R6 is calculated using this formula. Again, the natural frequency, the zero frequency, and the K here is 1, so we take 1, and the resistor R we have selected as 100 kilo ohm. And that will result in 35.33 kilo ohm. Now we are done with the first stage. The second stage is the realization of the low-pass filter, passive low-pass filter circuit that is realized by this C6 and the R6. We know R6, so how can we then go to the C6? That is then given by this formula. You see here the natural frequency of the second stage, which is this value, so 10,725, and that is then 1 over this R6 times C6, and C6 can be then calculated using this, so rewrite this formula. We know the omega, the natural frequency for the second stage, we know the R6, just calculate it, so we can now calculate that the capacitor must be 2.6399 nanofarad, so this is the value here. We will also calculate the cutoff frequency for our design, that is given by this expression. See the stop band frequency, the epsilon s, and natural the filter order. And if you substitute here the values, you get here 1.3 kilohertz. Okay. Let's now go to the simulation circuit. This is what we have calculated, and also the cutoff frequency. And this is the circuit in the SPICE simulator. You see here the 4 operational amplifiers. The resistors are each of them 100 kilo ohm, also the capacitors 100 nanofarads, and the other components we have calculated. Okay, let's now go to the simulation results. Now this is the Bode plot. You see again the same circuit here in the SPICE simulator. You see the Bode plot in blue, given the gain, the frequency here in the log scale, and the gain here in the vertical axis. What do we see? Now we see here that the DC gain is indeed 0 dB or 1, so that's according to the specifications. The cutoff frequency we had calculated was 1.3 kHz, and that's also shown here from the label, because at that frequency the gain is minus 3.01 dB, which is the definition of the cutoff frequency. That is perfect. We also see the passband gain, or that 1 kHz, which is actually what we had given in the specifications, is here minus 0. Let's say almost 6 dB, so minus 0.5935 dB, which is definitely smaller than the 1.5 dB what we was allowed to have. So this is indeed according to the specifications, but how do we calculate that actually? Because this is much smaller and different than the value. So how do we calculate that? Now we can calculate that using this formula. It was actually done similar way for the Chebyshev response, and there we had actually that we calculated a minimum. Now we calculate a maximum, and you see here that we need the filter order and the epsilon s. It's actually all shown here, and we also have the Fs and Fp also from the specifications. That actually, if you now substitute that in this formula, you get now 0.593553 dB. This is of course what we have also here, so that's indeed as we have seen in the simulations. We also see at 2 kHz, that was our stop band frequency, that the gain is minus 20 dB. So you see here indeed that the passband frequency, the stop band frequency, will indeed produce the exact required stop band attenuation of 20 dB or minus 20 dB in the gain values. We also see here the valley, which is due to that 0 location, so we see a very sharp decrease in the gain at 2.32 kHz, and then it goes up very fast and then approaches some peak, but it doesn't go above that minus 20 dB, which is of course fine because we want to stay below that minus 20 dB, and that happens at 4 kHz. And then again, when the frequency increases, this will go again, and then the gain will decrease. So we will see here that the specifications are met, and we have also calculated the required component values and the check for the cutoff frequency and the A max we have in our final design. So we can say here that it is indeed all correct. Alright, it was our example considering the inverse Chebyshev response active low pass filter. We have calculated the required component values and realized our circuit using the state variable filter circuit and verified our findings in the SPICE simulations. If you have any questions, please let me know in the comment section. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.